For our last talk, we have another merge talk. This is two talks that are about cryptography that can be done with kind of a single common Haar random state that all parties get to access. And to start this off, it'll be or Sattath for the first half.
Thanks. So you can hear me, right? Yeah. Okay. So the titles are Quantum Pseudorandomness from a Single Haar Random State by Boyang, Chen, Andrea, Coladangelo, and myself. And the other is Cryptography in the Common Haar Random State Model, Feasibility Results and Separations by Prabhanjan and Ananth, Aditya, Gulati, and Yao-Ting Lin, who present the second part. And we're not highlighting the differences, and I'll present mostly like the best of both papers in some sense. Feel free to look at the details in the papers themselves about the distinctions, etc. Okay. So I'll start with the motivation. Suppose I ask you if Alice and Bob has a random shared string, can they do cryptography? In the sense that like everybody could the string S is publicly available for everyone, and can that be used to do cryptography in an unconditional form? And one can easily see why this is possible. Actually, it was mentioned in some of the previous talks. And our question is, what happens if we kind of replace the random string in a natural analog, quantum analog? And what exactly do I mean? Here we have polynomially, like everybody get access to as like polynomially many copies as they wish of the same Haar random state. Right? So again, Alice and Bob have no secrets, right? Because everybody gets access to that. And we ask, is that useful for cryptography? And the answer is, yeah, it can be. There are cryptographic applications. We call this model the Common Haar Random State Model. And in particular, we show several applications. One of them will be bit commitment. I'll do this pretty fast because the previous two talks have already made that part. Commitments are like the digital analog of a locked box. Alice can put her bit B in a locked box, send it to Bob, and then in this part, there's like a property called hiding, right? Bob cannot learn anything about the bit inside the locked box. And in the reveal phase, Alice could send her key to Bob, and Bob could reveal the bit. And the property here that's important is binding, meaning Alice cannot change the bit from, say, if she committed to 0, she cannot change her mind, reveal 1. Okay. And I'm going to give a short reminder about the impossibility result because I think it provides some intuition. So it's well known, our result says that any quantum bit commitment that is perfectly hiding is not statistically binding. Actually, the proof is so short that I'll actually redo it. So what do we mean that it's perfectly hiding? It means that Bob's state, when Alice commits to 0, let's call that row 0, and row 1, when she commits to 1, must be the same. Right? That means that it's hiding. And let's look at the purified states that Alice, like the shared state that they have in case of when Alice commits to 0 and 1. And let's recall that Ullmann's theorem guarantees that for any two such states that have the same, since row 0 equals row 1, it means that there's a unitary acting only on Alice's side that maps psi 0 to psi 1. So how will she kind of change her mind? She'll always commit to 0. So at this point, she has psi, like the shared state is psi 0. And if she wants to open to 1, she'll apply that unitary and continue from there. Right? So that's kind of very easy to see that there's no such thing, right? There's no perfectly hiding and binding scheme. Okay. And what we show is that in the CHRS model, there exists perfectly hiding and statistically binding bit commitment. Okay, meaning no matter what's her computational, like Alice's computational power, as long as she has only polynomially many copies, she won't be able to, the scheme will be binding. And what's the intuition? That's at least my interpretation. I don't know. Yeah, hopefully many of the other authors here will agree that the intuition is that Alice has only polynomially many copies. Even though there exists a unitary that maps psi 0 to psi 1, since she has only polynomially many copies to the Haar random state, she won't be able to kind of learn what the unitary she needs to apply is, right? And therefore, she won't be able to kind of violate binding. Okay, so that's, I think, the intuition. We won't discuss how exactly the construction works. It's very nice because, like, in some sense, Barak already kind of showed us the construction. Or both of you, I guess, guys, show the construction. And essentially, we use a construction which shows that single copy PRS implies commitments, and actually many other like application, and mostly like oblivious transfer and multi-party computation. So we won't deal with that. We will only concentrate on showing that we can construct single copy PRS, and I'll explain what that is later. Okay. So again, our results are kind of discuss certain forms of pseudorandomness, and specifically two forms of quantum pseudorandomness that I'll discuss. So pseudorandom states are a family of states phi k, such that phi k can be generated efficiently for every k, and an adversary which receives polynomially many copies of phi k or polynomially many copies from a truly Haar random state cannot tell apart which is which, right? Look, so a random phi k, right, polynomially many copies of it, looks just like a polynomially many copies of a Haar random state. An important variant is called one PRS or single copy PRS. In here, the adversary gets only one copy. Okay? And notice that in the right-hand side, since it's only one copy, it's essentially saying that this single state from the family is distributed like the maximally mixed state. And for that to be non-trivial, we need that this length of the state, or the stretch, satisfies that m, the size of the state, is longer than n, the key size. Okay. Then it becomes non-trivial to do. So now, what happens in the CHRS model? It's exactly the same definition as before, right? Here's the previous slide, but now we add this additional Haar random state that all the parties get access to, including the adversary, right? Okay. So you need the Haar random state to generate the pseudorandom state, and the adversary gets access also to that Haar random state, like psi. Okay. So what do we know about this model? So we show two main results. One is that one PRS exists unconditionally in the CHRS model, right? As long as the adversary has polynomially many copies, no matter what's the computational time, the adversary won't be able to tell apart whether it's pseudorandom or random. And the second result, and which is maybe surprising, that pseudorandom states do not exist in this model, okay, relative to some oracle. And and I think this is like a life achievement of mine in some sense, like a life goal of mine. So my name is Or, right? That's my first name, and somehow of course we use the quantum Or lemma. And,
Okay, thanks, Or. So I'm Yao-Ting, and I'll continue to tell you about our construction of one PRS. So it's very simple. On an n-bit key k and 1 copy of m qubit common Haar state psi, we'll simply apply poly z operators to the common Haar state. So the output denoted by psi k is equal to z to the k times psi, where z to the k here is a shorthand for the tensor product of poly z operators controlled by the key. And the common Haar state has to be strictly longer than the key. Yeah, so it's easy to see that, okay, it's efficient and satisfies the stretch property. And our construction actually works for common Haar state of any length, as long as it's not shorter than the key. And I'll briefly explain our idea behind the proof. So remember, we're considering statistical security. So we have to show the following states are close in trace distance. So in the real case, the distinguisher gets 1 copy of psi k on a random key as the challenge state, along with t copies of the common Haar state, where t is an arbitrary polynomial. Whereas in the ideal case, the challenge state is a Haar random state phi, which is independent of the common Haar state. So intuitively, the question is whether applying random poly z to the first copy is able to decorrelate it from the other t copies. And their trace distance turns out to be order t squared by 2 to the n, where n is the key length. And this bound is independent of the length of the common Haar state. And our proof relies on facts about symmetric subspace. And it has only elementary combinatorial arguments. So the details can be found in our paper. Yeah. And as Or mentioned, it's impossible to achieve statistically secure PRS in the CHRS model. So maybe let's first recall how we can information theoretically break any classical PRG. So given a string y, whether it's a random element in the output space or g of x on a random input x, then we can simply check whether y is in the range of the PRG. Because of the stretch property, the range of the PRG will be sparse in the output space. So we'll have a constant success probability. And now, let's say we're given a PRS construction that we want to break, which uses p copies of the common Haar state to generate the output. So there could be 2 to the n different output state, each of which corresponds to a different key. But now, the distinguisher is only given polynomially many copies of the challenge state. So we cannot naively compare the challenge state to the output state one by one. Then we have to rely on the quantum Or lemma, which says the following. So let pi 1 to pi n be a set of projectors, and let epsilon and delta be some small numbers, and rho be a state that satisfies one of the following 2 cases. In the true case, there will be some index I, such that the trace of pi I times rho is at least 1 minus epsilon. In the false case, for any indices, the trace of pi I times rho is at most delta. Then the quantum Or lemma tells us that there is some circuit that only uses 1 copy of rho to distinguish between the 2 cases. In particular, in the true case, it accepts with probability at least 1 minus epsilon squared over 7. In the false case, it accepts with probability at most for delta n. So here's our distinguisher. It uses 10 copies of the challenge state and 10 NP copies of the common Haar state. So we'll let rho to be the tensor product of all these input states. And then for each key, we'll define pi k to be the projector corresponding to the following event, that all 10n swap tests between the challenge state and phi k succeed. And then we'll run the circuit in the quantum Or lemma on input rho with respect to this set of projectors. And we show that using a QP-based machine oracle, this distinguisher can run in polynomial time. So let's see why this works. So if the challenge state equals psi k for some k, then all the swap tests will succeed. So our distinguisher will accept with probability at least 1/7. And in the other case, we can show by the concentration of the Haar measure, we can show the following events happens with overwhelming probability. That for all key, the trace of pi k times rho is exponentially small. So our distinguisher will accept with a negligible probability. So that's how it distinguishes between the two cases. And combining these two results, we'll have the black box separation between one PRS and PRS. So prior to our work, we know that pseudo-random states do not imply one-way functions in a black box way. But pseudo-random states already imply quantum cryptography. So there are many new primitives weaker than one-way functions have been defined, which form the world of microcrypt. But still, in microcrypt, the relation between primitives is not fully discovered. In particular, we don't know whether one PRS is weaker than or equivalent to PRS. And in this work, we use the CHRS model to answer this question. So more formally, we show that relative to a family of common Haar random state and an oracle to a QP-space machine, one PRS exists while PRS does not. So this is one of the first separations inside microcrypt. And the CHRS model turns out to be useful for other problems. So a very recent work by Bostanchi, Chen, and Nehoram showed a separation between one PRS and one-way state generator, where they also used the CHRS model in their proof. And we also studied the impossibility of statistically secure QCCC primitives in the CHRS model, where QCCC stands for quantum computation classical communication. So QCCC primitives have the following form. So basically, all parties have access to the common Haar states, but are only allowed to communicate via classical channels. So you can think of the scenario where quantum computer owners, such as companies or governments, communicate through the internet. And interesting examples include bit commitment and key agreement or key exchange. And I want to remind you that the bit commitment constructed from one PRS requires quantum communication. So this is not a QCCC primitive. And our main technical tool is the LOCC Haar indistinguishability. So let's consider the following two experiments. In the first one, the referee in the middle will send T copies of a Haar state psi A to Alice and T copies of another Haar state psi B to Bob. That Alice and Bob can communicate arbitrarily. In the second experiment, the referee will instead send T copies of the same Haar state to Alice and Bob. So if they can do quantum communication, then Alice can simply send her state to Bob to perform a swap test. So this task is easy. However, if Alice and Bob do not share any entanglement and they can only do classical communication, even if they are computationally unbounded, their advantage is at most order t squared by 2 to the n, where n is the length of the Haar states. So if t is a polynomial, then this is negligible. So this provides us a framework for proving impossibilities in the CHRS model. So let's say we want to prove the impossibility of some statistically secure QCCC primitive. Then for contradiction, we'll assume such a protocol exists. Then we can define a new protocol in a plane model simply by replacing the common Haar state with two independent Haar state, psi A and psi B. Because now they are independent, so Alice and Bob can sample the Haar state by themselves. And by the LOCC Haar indistinguishability, this new protocol in the plane model remains correct and statistically secure. But this is a contradiction. So that's how we prove the impossibility in the CHRS model. All right, so in summary, we define the common Haar random state model, which is a quantum analog of the classical common random string model. And we show some statistically secure primitives, which are impossible in the plane model or even in the common random string model exist in the CHRS model. And we also prove the black box separation between one PRS and PRS. And in our paper, we have some additional results, which I don't have time to talk about today. So the construction of one PRS is still secure when the distinguisher is given a few more copies of the challenge state. And we also show the black box separation between PRFS with long output length and QCCC key agreement or commitments. And in the paper by Orr and others, so they have a very nice generic lifting theorem, which can lift separations relative to common Haar random states, so which is a isometry oracle, to a more general separation relative to a unitary and its inverse. And that's it. Thanks.
So I think originally your separation is isometry 1, but now do you have oracle, unitary oracle separation?
Is there a unitary
Yeah,
separation?
unitary
So
separation.
actually it's kind of weird, but there were 3 papers showing it in various different ways. I've even heard of a 4th that uses another technique. It's kind of, there are many ways to do it. And yeah, I guess the answer is yes.
So one
And
PR,
you know, these are the papers that are public at
yeah,
least.
yeah. So one PRS and PRS is also separated in unitary oracle.
Yeah, unitary oracle. I
Okay,
can
okay.
say a word. I think in all the papers, it's a variant of this idea, where the unitary maps 0 to psi to 0, and identity on the rest. This is kind of the. And there are some variants. Like they use slightly different oracle. I'm not. Yeah, I don't want to get into the details, but all kind of slight modifications of this idea. Questions?